Welcome to MRL. In this learning session, we'll learn a few important theorems of chords and also arcs and cyclic quadrilateral discussed in the Ganita Manjari 9th standard NCERT textbook. Now here we have the first theorem here. The angle subtended by an arc at the center of a circle is double the angle subtended by the same arc at the circumference. Now the theorem is very clear. We are given a circle with center O and arc AB is an arc. The arc AB subtends an angle AOB at the center, which is known as the central angle, and the same arc AB subtends an angle APB at the circumference. So we are given circle with center O, arc is AB, subtends angle AOB at the center and APB at the circumference. Now we have to prove that angle AOB is 2 times angle APB. Now for that we will have to go for a construction. Join PO and extend it to D. Join PO and extend it to D. Now we get two triangles here, triangle AOP and triangle BOP. And if you take triangle BOP, the angle 3 and angle 4 are equal because they are angles opposite to equal sides OP and OB. And also angle BOD, which is angle phi here, is equal to the sum of the interior opposite angles, that is angle 3 and angle 4. So we have angle phi is equal to angle 3 plus angle 4. But as I have already told you, angle 3 and angle 4 are equal. Therefore angle 4 is also equal to angle 3, and therefore angle phi becomes angle 3 plus angle 3. That means 2 times angle 3. Let us call this as 1. Again, if you take the triangle AOP, and in that OA and OP are equal, angle 1 is equal to angle 2. That means angle 1 is equal to angle 2, and also angle AOD, that is angle 6, is equal to angle 1 plus angle 2, because exterior angle is equal to sum of interior opposite angles. Therefore we have angle 6 is equal to angle 1 plus angle 2. Now as I have told you, angle 1 and angle 2 are equal, therefore I can replace angle 2 by angle 1. Therefore angle 6 is equal to 2 times angle 1, and let us call this as equation 2. Now let us add 1 and 2. When we add 1 and 2, we are adding LHS and RHS. LHS is angle phi plus angle 6, and RHS is 2 times angle 3 and 2 times angle 1. So it is 2 times angle 1 plus 2 times angle 3. Now what is common in this is 2. Taking 2 outside, we get in the bracket angle 1 plus angle 3. But angle 1 plus angle 3, if you observe, it is angle APB, and therefore replacing it I get 2 times angle APB. That means angle AOB is equal to 2 times angle APB. So the conclusion is very simple. The angle subtended by an arc at the center is double the angle subtended by the same arc at the circumference, and that is the proof, and we have proved it. Okay, let us go to the next example. Now again a theorem. Now here in this theorem, AB and D are two chords. AB and D are two chords of a circle with center C. This is center C here, and assuming that AB is greater than DE, then the distance from C, if AB is greater than DE, then the distance from C to AB is less than the distance from C to DE. The meaning is, we are given a circle with center C, AB is a chord, DE is a chord, AB is a chord greater than the chord DE, then we have to understand that, or we have to prove that the distance of the chord AB from center is less than the distance of the chord DE from the center. From the center. That means the greater the chord, lesser the distance, the smaller the chord, then greater the distance from the center. So let us understand how to do this. Now we are given a circle with center C, AB and DE are chords. Chord AB is greater than chord DE, and we have to prove that the distance of distance of AB from C is less than the distance of the chord DE from C. Or we have to prove that CF is less than CZ, because CF is the perpendicular distance of the chord AB and CG is the perpendicular distance of the chord DE from center. We have to prove that CF is less than CG. Now let us understand. Now let us go for the construction. Join CA and CD. Join CA and CD, and in triangle AFC, AC square is equal to CF square, that is AC square is equal to CF square and AF plus AF square by Pythagoras theorem. So AC square is equal to CF square plus AC square by Pythagoras theorem. And also in triangle DGC we have DCG, we have DC square is equal to CG square plus DG square by Pythagoras theorem. Now we know that AC and GD and CD, AC and CD are radii, AC and CD are equal, therefore I can equate the RHS. We have got AC square is equal to CF square plus AF square, CD is equal to CG square plus DG square, but now we know that AC and CD are equal, therefore AC square is equal to CD square, and therefore we can equate the RHS, that is CF square plus AF square is equal to CG square plus DG square. But let us understand here that AB is greater than D, that is given to us the chord AB is greater than chord DE, half of chord AB is A by 2, half of chord DE is D by 2, that means half of chord AB is AF and DE is DG, and that means AF is greater than DG, because F is the midpoint of AB and G is the midpoint of DE, because when a perpendicular is drawn from the center to any chord, it bisects the chord, therefore AF and BF are equal, DG and G are equal, and therefore AF is greater than DG, and it is correct. Now putting this value of AF and DG here, we find that AF square and DG square are AF square is greater than DG square. If AF square is greater than DG square but natural, CF square is less than CG square, or CF is less than DG. CF square is less than DG square, CF square is less than DG square, or CF is less than DG, and therefore the conclusion is the greater chord has a shorter distance from the center. So try to understand that. So that is the theorem for you. Now coming to the next theorem. The theorem is, if a line segment joining 2 points subtend equal angles in a segment, then the 4 points are concyclic. So let us understand this. AB, see, we are given a circle with center O. AB is what you call a line segment, and it joins 2 points. That AB is joined, therefore it forms a line segment, or you can even call it as a chord. It subtends an angle ACB at the circumference. ACB is the circumference, or ACB is the angle in the segment, in the bigger segment here, or a major segment here, and also ADB is another angle in the same segment. So we have got ACB and ADB are two angles in the same segment. Now if that is true, then the points ACDB are concyclic, or all the 4 points, that is ACDB, lie on the same circle. Again I'll repeat, if a line segment, any line segment joining 2 points subtend equal angles, see, angle ACB and ADB equal angles in a segment, then the 4 points are concyclic. ACB and ADB are in the same segment, that is major segment, then the points A, C, D and B are concyclic, rather they lie on the same circle. So now how to prove this? Now we are given a circle with center O. AB, please mark it as O. AB is a line segment. Angle ACB and ADB are angles in the same segment, that is major segment here. Now we have to prove that ACDB are concyclic or lie on the same circle. Now let us take, now if since they are in the same segment, we are given that ACB and ADB are equal. ACB and ADB are equal angles. So ACB and ADB are equal angles. Let us call this as 1. Now suppose that the circle does not pass through D, it does not pass through the point D, but let us say it passes through the point E. Let us assume that it is passing through point E. It means that ACEB, that means angle ACB and angle AEB are equal. That is the point number 2. That is equation 2. But what do we see here in 1 and 2 now? ACB is equal to ADB. ACB is also equal to AB. That means ACB and AB are equal angle. That means ACB is equal to ADB. ACB is equal to AB. That means ADB, angle ADB is equal to angle AEB. ADB equal to angle AEB. That is possible only when E coincides with D. It means that the circle is actually not passing through E, it is passing through D only, and therefore I have written here, it is possible only if the point E coincides with D, therefore the circle passes through the point D, and the points A, C, D and E are concyclic or lie on the same circle. So that is how we prove it, by assuming by taking a contradiction and then proving it to be what is assumed is wrong and what is not assumed is correct. So this is the method of solving the theorem. So try to understand these theorems. Let us proceed further with the other aspects of the study of circles. Now the next important point of our study is cyclic quadrilateral. A quadrilateral, the vertices of which are concyclic or lie on a circle, is called cyclic quadrilateral. A quadrilateral, the sides of which form the chords of a circle, is called a cyclic quadrilateral. ABCD is the cyclic quadrilateral here. Let me explain this to you. Now ABCD is a cyclic quadrilateral because the vertices of the quadrilateral lie on the circle, or the vertices of the quadrilateral are concyclic, and also the sides of the quadrilateral form the chords of a circle, and therefore the quadrilateral is cyclic. Remember that. The opposite angles of a cyclic quadrilateral are supplementary. That means angle A plus angle C is 180, angle B and angle D is also equal to 180. That is, the opposite angles of a cyclic quadrilateral are supplementary. The exterior angle of a cyclic quadrilateral is equal to the interior opposite angle, and it's very important property here. Now if you see here, ABCD is the cyclic quadrilateral, and when I extend AB to E, I get exterior angle, that is CBE. Now the angle CBE, which is the exterior angle of the cyclic quadrilateral, is equal to the interior opposite angle. The opposite to this angle is this, therefore angle ADC is equal to angle CBE, and that is what you have to remember. That is, angle CBE is equal to angle ADC. Very important property again. A quadrilateral in which the opposite angles are supplementary is a cyclic quadrilateral. Now if you look here, if you take this quadrilateral ABCD, this will be a cyclic quadrilateral if angle A plus angle C is 180, or angle B plus angle D is equal to 180. Now having understood what is a cyclic quadrilateral and the properties of cyclic quadrilateral, let us prove those properties of cyclic quadrilateral in the form of a theorem. We have the first theorem here. The sum of either pair of opposite angles of a cyclic quadrilateral is 180 degrees. It means that we are given a circle with center O. ABCD is a cyclic quadrilateral. Now we have learned the property that angle A plus angle C, the opposite angles of a cyclic quadrilateral, are supplementary, and that is what we have to prove here. So now what is given to us? Circle with center O, ABCD is a cyclic quadrilateral. Now we have to prove that angle A plus angle C is 180, angle B is equal to angle D is equal to 180. Now construction required is join OB and OD. Join OB and OD. Now proof is angle BOD plus this is angle BOD here, this is BOD, and the reflex angle BOD, that means both the angles here, angle BOD and reflex angle BOD, as we know it is 360 degrees because the angle at the point is 360 degrees. Okay, so for angle BOD plus angle reflex angle BOD is equal to 360, and let us understand that. Now angle BCD, it is half of angle of BOD. It is half of angle of BOD because we know that BD is the arc, and the arc BD subtends an angle at the center and also at the circumference. The angle at the center is double the angle at the circumference. Therefore, the angle at the circumference is half of the angle at the center, that is central angle, that is angle BOD, and therefore angle BCD is equal to half of angle BOD. Let us call this as 1. And for the same reason, angle BAD is half of reflex angle BOD, and okay, for the same reason, so let us call this as 2. That is equation number 2. Now the center subtended by the same arc, okay, this is already I have told you. Now adding this 1 and 2, you add 1 and 2, that means add angle BCD and BAD. When we add BCD and BAD, we get half of angle BOD and half of reflex angle BOD, and therefore angle BCD plus angle BAD is equal to 180 degrees. That means we have proved that BCD plus BAD is 180 degrees. Now we have one pair of opposite angles equal to 180 degrees, but we know that all the four angles of a quadrilateral is 360 degrees. If angle A plus angle C is 180, but natural, angle B plus angle D must also be equal to 180 degrees. Therefore, the opposite angles of a cyclic quadrilateral are supplementary. So that is what you have to understand and remember. Now coming to the next again important property, the theorem there again. If the sum of a pair of opposite angles of a quadrilateral is 180 degrees, then the quadrilateral is a cyclic quadrilateral. Now again let me explain this to you. We are given a quadrilateral ABCD. Now if angle A and angle C, the sum of angle A plus angle C is 180, or angle B plus angle D is 180, then ABCD, which is a quadrilateral, becomes a cyclic quadrilateral. That is the meaning of that. If the sum of a pair of opposite angles of a quadrilateral is 180 degrees, then the quadrilateral is cyclic. So let us try to prove this property. Now we are given ABCD is a quadrilateral, angle B plus angle D is 180. Now we have to prove that ABCD is cyclic. Now let us suppose here that ABCD is not a cyclic quadrilateral. That means D does not lie on the circle. Let E lie on the circle. Then ABCE is cyclic quadrilateral. If ABC is cyclic quadrilateral, then angle B plus angle E is equal to 180, because the opposite angles of a cyclic quadrilateral is supplementary. Now we are given angle B plus angle D is equal to 180. Now we have shown that angle B plus angle E is equal to 180. That means angle B plus angle D is equal to angle B plus angle E is equal to 180. It means that the point E, please understand here, the point E should coincide with D if this equality has to be true. Therefore, it is not the quadrilateral BCEA or ABCE which is cyclic. It is ABCD, which ABCD is a quadrilateral where the points lie on the circle, and therefore the quadrilateral ABCD is a cyclic quadrilateral. That's what I have written here. Or the point E coincide with point D, because E and D are the same point, therefore ABCD is a cyclic quadrilateral. So that is what is the proof of this theorem. Now coming to the next point, how many circles can be drawn passing through one point? Innumerable. If you see the diagram here, I have a point P. Through P there is circle C1 passing, C2 passing, C3 passing, C4 passing, C5 passing. So many circles pass through a single point, and therefore many circles pass through a single point, or infinite circles pass through a point or single point. So therefore the number of circles that pass through one point are infinite circles. Now how many circles pass through 2 points now? We have 2 points here, A and B. So many circles pass through. Again, if you observe here, we have got C1, C2, C3, C4. So many circles pass through point through the 2 points AB. Now, if you observe here, point A and B are 2 points. AB is joined. Therefore, AB is the line segment here. And if I draw a perpendicular bisector to AB and take any point C, D, E, G, and F. Now, if you observe here, AE, the distance AE is equal to BE. That means E is at the same distance as E and B. Therefore, if I take E as the center and draw a circle, it passes through AB. Now if I take G is at the same distance from A and B. That means AG and BG are equal, and therefore AG becomes the radius, BG also becomes the radius. So if I take this as a center and draw a circle, then the circle will pass through AB. So like that, we can have innumerable points on the perpendicular bisector of AB, which are the centers of the circle which pass through A and B. So therefore remember, the points C, D, E, F, G are the equidistant from A and B and are the centers of the circles through A and B. Therefore innumerable circles can be drawn passing through 2 points. Remember that. And one more important thing is, the points are, all these points, that is F, C, D, E, F, G are equidistant from the points A and B, and we can call them as radii of the different circles which pass through A and B. And one more thing is, if the distance from the center, if you take the point C here, if that is the center of AB, if I take point D, then we have one circle, then E another circle, G another circle. But you see that the curve slowly decreases as we go away from the center, away from the line AB or the line segment AB. The curve of the circle decreases. So this is more curved, this is less curved, this is further less curved. So as the distance, that is as the distance from the center increases, or as the radius increases, then the curve of the circle also decreases. So please remember that. Now coming to the next point, the number of circles that pass through 3 non-collinear points. We have 3 non-collinear points here, that is point A, B and C are 3 non-collinear points. Now we have to find how many circles pass through these 3 non-collinear points A, B and C. Now we are given A, B and C are 3 non-collinear points. A, B and C are joined. We join AB and AC and we draw the perpendicular bisectors RS and also PQ. RS is a perpendicular bisector drawn to AB, and PQ is the perpendicular bisector drawn to AC. And once we draw the perpendicular bisector, if you take a point O on that, then OC and OA are equal, OC and OB are equal. Please understand here, OC and OA are equal and OC and OB are equal. Please understand, OC and OB are equal. The reason is the point O is at equidistant from point A and C, and also equidistant from C and B, and therefore OA, OC and OB, all the three of them are equal. Now we can take this point O as a center and the radius as OA or OC or OB and draw a circle. We find that the circle passes through the three non-collinear points. It passes through the three non-collinear points. So O is the only center possible, because when two lines intersect, because we have the perpendicular bisector PQ and RS intersecting at a point, and we know that two lines can intersect in only one point, and therefore only one center is possible, and with that center, with that only one center, we can draw only one circle passing through the three non-collinear points A, B and C. The conclusion is only one circle is possible, or only one circle passes through the three non-collinear points. And another very important thing what you have to understand here is that this radius, the circle is which passes through the three points, non-collinear points, form a triangle, and therefore it is called as a circumcircle. The circle passing through the three non-collinear points or the three vertices of the triangle is called circumcircle. And this center from where the circle is drawn, that center is called as circumcenter, and the radius which is used to draw the circumcircle is known as circumradius. Try to remember that, and that is exactly what I have given here. Circumcircle, the circle that passes through three non-collinear points which are also the vertices of a triangle, is called as circumcircle. Circumcenter, the center of a circumcircle, is called as circumcenter, and the distance from circumcenter to any one vertex of the triangle is known as circumradius. Now the question arises, if a circumcenter is located, if the circumcenter is located here, now where does this, where this point lies, whether it is inside the triangle, whether it is outside the triangle, where it lies, because we know that there are different types of triangles. We have got acute angle triangle, obtuse angle triangle, right angle triangle. So if you take acute angle triangle, the circumcenter lies inside the triangle. It lies inside the triangle. If you take an obtuse angle triangle, it lies outside the triangle. Say like the point O, which is the center, is lying outside this triangle. And if you take a right angle triangle, it is exactly the midpoint of the hypotenuse. And this will be more clear to you when I discuss the constructions in the questions in the various what you call exercises of the textbook. There will understand how the circumcenter lies inside, outside, or at the midpoint of the right hand triangle. We have an exercise where the constructions are there. When I complete those constructions, this point will be more clear. Okay, but still you remember as to what happens in an acute angle triangle. The circumcenter is inside. For obtuse angle triangle, it is outside, and for right angle triangle, it is the midpoint of the hypotenuse. Now coming to the next and very important discussion, that is there is one and only one circle passing through three given non-collinear points. We have to prove this, and rather give a logical proof of the condition that there is only one circle possible passing through non-collinear points. Now let us take A, B and C. A, B and C are three non-collinear points, and we have to prove that only one circle passes through A, B and C. And for that, let us draw perpendicular bisector PQ and RS to the line segment AB and BC, and the two perpendicular bisector intersect at point O. And AB and BC form the chords of the circle, and they are perpendicular to the chords, and therefore you find that the perpendicular bisector pass through a point O, and that point O has to be the center, of the circle. Now the two lines of PQ and RS can intersect in only one point, and therefore O is the only point and the only center, and only one circle is possible to be drawn passing through the 3 points A, B and C, and therefore the conclusion is only one circle can pass through three non-collinear points. So remember that is exactly what you have to understand. So this was the discussion on the different theorems, and also the discussion on cyclic quadrilateral, the properties of cyclic quadrilateral. So almost all the aspects of the circles and the chords is discussed in different videos of this particular chapter. So please go through all the videos, and further I'll be giving you the solutions of the different exercises and the end of the chapter exercises for you to understand the basics clearly. Okay, so note down, learn, practice, and okay, in the notebook as it is you are writing, so keep it as a reference for your future use. Thank you.